By the end of its run, Project Whirlwind had consumed $5 million, spending nearly $1 million a year at its peak. And after all that, it completely failed to deliver the machine the United States Navy had actually paid for. But this multi-million-dollar failure inadvertently created something far more valuable. In attempting to build a flight simulator, engineers hit a fundamental wall in computer science, the memory bottleneck. Breaking through it gave birth to the technology that made every modern computer possible. The story begins in 1944, when the Office of Naval Research commissioned the Massachusetts Institute of Technology to build the Airplane Stability and Control Analyzer. This was originally meant to be an analog electromechanical flight simulator, but in 1946, project leader Jay Forrester saw the ENIAC computer and realized analog systems simply could not keep up with the mathematics of real-time flight simulation. Forrester pivoted the entire program, deciding instead to build a high-speed, real-time digital computer. He named the new effort Project Whirlwind. Whirlwind was designed as a 16-bit machine, operating in bit parallel mode. This architecture allowed it to perform 20,000 operations per second, making it incredibly fast for its era. The exact physical footprint of the machine remains a matter of historical debate. Some records state it used around 4,500 vacuum tubes, covering 2,000 square feet, while other engineering sources cite up to 12,500 tubes, packed into 3,000 square feet. Regardless of the exact count, the hardware was massive, and the maintenance was grueling. As the machine came online in late 1949, Forrester and his team hit a critical bottleneck. Whirlwind's processors were fast, but its memory was not. The computer relied on electrostatic Williams tubes to store data. These tubes were highly unreliable and had slow access times of roughly 30 microseconds. The processor spent most of its time sitting idle, waiting for data to arrive. As scope crept upward and the memory issue persisted, the Navy began to lose interest. Facing the loss of funding, the project was only kept alive when the United States Air Force intervened, looking to repurpose Whirlwind's technology for a new radar-based air defense network. To save Whirlwind, Forrester needed a completely new way to store data. In June 1949, he began documenting a concept for coincident current magnetic core memory. By threading a grid of wires through tiny ferrite rings, binary data could be stored magnetically, allowing for high-speed, reliable retrieval. But Forrester was not the only one trying to solve this problem. Over at Harvard, physicist Anne Wang had developed a write-after-read cycle in 1948, solving the issue of destructive readout. Meanwhile, RCA engineer Jan Reichman was independently developing his own core memory system. The precise attribution of who truly invented core memory would become entangled in years of contested patent claims between multiple inventors. Despite the looming patent battles, the MIT team pushed forward. In October 1950, graduate student William Pappian built the first operational core memory prototype. By August 8, 1953, a full magnetic core memory array was finally installed and operating on Whirlwind. The upgrade completely transformed the machine. Whirlwind successfully demonstrated the real-time tracking of aircraft interception courses, proving it could process complex data instantly. This success cemented Whirlwind as the direct prototype for the Air Force's SAGE early warning system. Years later, the commercial value of these inventions became undeniable, with IBM eventually paying MIT $13 million in 1964 for Forrester's patent rights. Project Whirlwind never became the analog flight simulator the Navy originally asked for, but by attempting to build a machine that could process reality as it happened, Jay Forrester and his team were forced to solve the speed limit of early computing. Magnetic core memory solved the data retrieval bottleneck, making true random access memory possible. A $5 million military overrun ended up laying the foundational architecture for the digital world we live in today.